Today I'm going to present our work on evasion attacks, which we call morphing in the dark. And this is work done with my student Han Tang and Huang Yu. So in the evasion attacks, starting from malicious sample X, that is being rejected by detectors. So attacker want to find evading samples. That is, the X prime is accepted by the detectors, and yet it retains the malicious properties. So let's look at the motivating examples. In these motivating examples, the attackers want to send a malicious PDF files as attachment to the victims. However, the email server will block this, have a malware detector in place and block these emails. So the attacker want to evade the detectors. That is to find another malicious PDF that is being accepted by these particular malware detectors. The attacker can get a feedback on these malware detectors by simply sending the PDF files back to the attackers. So from that, he get a feedback on whether the malware X prime is being accepted or rejected. So we assume that the attacker doesn't know the internal mechanisms of these malware detectors. So it's the malware detectors function as a black box to the detectors. And the number of access to the black box is limited. This because sending the emails to the server is very expensive. Also, if the attacker sends too many emails, then the email server will simply block these particular attackers. So as we've attended keynotes, there are a lot of quite extensive work on this area. So in the machine learning, this is also known as adversarial examples. So we have seen quite a number of examples in the previous sessions. And in the setting of image watermarking, image watermarking removal, there's also evasion. In this case, the watermark detectors is a publicly available black box. And they are also for malware detection and many more. Okay. So many such evasion attacks, they heavily rely on the domain knowledge. For examples, like the internal mechanism of the detectors and domain representations. For examples, evasion attacks may from a set of samples find a gradient or average samples in the evasion algorithms. And such averaging mechanism may not be present in some domain. For example, malware, right? If you have a set of malwares, then it's not very clear what we mean by the average or the gradient of the malwares. And the malware detectors may just simply output a binary decision saying yes or no. However, many evasion attacks make use of assume that the black box detector provide a real numbers feedback on the confidence levels, and they base on these confidence levels in the evasion process. So our goal is to investigate evasion attacks under a very generic model that we can separate the algorithmic aspects and the domain-specific mechanisms. And of course, we want to consider about binary output detectors. Okay. So we will propose a model of evasion in the dark. So in our models, we assume the attacker has access to 3 black boxes. The first one is the detector that he wants to evade. Okay. So in our malicious email examples, this detector is the malware detectors. Okay. And we also assume that the attacker has access to a tester which provides a ground truth of whether a sample is malicious or not. In the malicious email examples, this tester could be a sandbox that takes a sample as input, process it, run it, and check whether any suspicious system call have been made. So we can see that the tester is a very expensive process. Potentially, it could also involve a human in the loop, some manual process in the tester. But anyway, the tester will provide ground truth of whether a sample is malicious or not. We also assume that the attacker have access to a black box of a morpher. This morpher take in a sample X and make some modification according to specified by the seed R and output morph samples. So with these three black boxes, then the attacker can carry out the evasion by morphing. That means that he can adaptively query the black box so as to find evading samples. Okay. So this is an illustration of the process. So on the left are the sample that declared to be malicious by the tester. This is the ground truth. Okay. And on the right are the samples that's been accepted by the detectors. For evasions, the attacker actually want to find an intersection of these two. That means that a sample that is malicious and yet accepted by the detectors. The attacker goals now is to find a morphing path, a path of morphing, successive morphing, from the starting samples that he have to an evading samples. Okay. So some remarks. The output of the detector and tester are binary. Okay. The implication is that from the samples and the output from the black box, we don't have a good idea of the relative positions of these samples to the evading regions. Also, the query consists of two parts. One is the samples and a seed. So in this example, the sample is a PDF file. The morph sample could be the PDF file with some object of deleted or replaced, specified as by the seed. So we assume that the attacker might not know the relationship between R, the input, and the morph samples. So in some sense, to the attacker, the morpher perform a random morphing. So he doesn't know what he will get until the morphing is done. Okay. And such uncertainty capture a situation where the attacker is unable to exploit domain knowledge to manipulate the samples. So, for example, the morpher could be is an output of a learning process, or is using some domain knowledge that the attacker is unable to exploit. So by that, given two samples X and Y, so it's not clear that can we use a morpher to find the average of this X and Y. So although we say to the attacker the morphing is random, but the morpher algorithm is deterministic. The algorithm is deterministic. Thus, the morphing is repeatable if we supply it with the same sequence of seeds. Okay. So such a model of evasion using these three black boxes is not new, have been studied before, particularly in NDSS 2016. She gave attacks on PDF malware using the three black boxes, the detector, the tester, and the morpher. However, there are some differences in our models. First is that they assume that the detector return a real value confidence level that gives some indication of the distance from the sample from the detection boundary. Also, they introduced an interesting property called trace replay. That means that a sequence of morphing steps could produce similar effect on different samples. For example, if a particular trace when applied to a sample X produce evading samples, then with good chances when you apply to another samples, you also produce evading samples. So their algorithm make use of these properties. Okay. So we do in our model we don't assume this. Okay. So let me give our proposed algorithms. The first thing we want to solve is the black box nature, where the black box only output a binary output of accept or reject. And to overcome this, we define something called flipping distance. Okay. So basically, if we are given a path of successively morphed samples, we define the malicious flipping distance to be the distance where the sample first switch from malicious to benign. First switch from malicious to benign. So in the picture there, you can see the red color line, red color indicate the malice flipping distance. Likewise, we can define the reject flipping distance with a distance where the sample first switch from reject to accept. Okay. So looking at the picture, looking at the bottom picture, bottom path, you can notice that if the malice flipping distance is larger than the reject flipping distance, then we will have an evading sample in the path, right? So that means that the starting from the starting samples, it start to get accepted by the detector before he turn to benign. So with this distance, then we can assign a numeric state to each sample. Okay, such a numeric state could be useful in the search process. So for a sample, ideally we can assign the probability that a random path starting from this sample S is evading as the state. So from this state, then we can, in the searching algorithm, for example, we can always choose one with a higher probabilities. Okay. However, it's very difficult to estimate these properties, right? Given the black box access, how do we estimate these probabilities? So alternatively, we can assign the expected gap to be the state of this sample. And this is easier to estimate. For example, we can generate a few random paths, and from that random path, give an estimate of the expected gap. Okay. And intuitively, a smaller gap implies that the sample have a higher chance of generating evading path. From here, then we can derive our search algorithms. The main idea is quite simple. Okay, first, start from the starting samples, the sample that we want to evade. We generate a number of random paths, and from the random path, we can calculate estimate the expected gaps, and from there we choose the one that is a minimum, the smallest. So in this example, it's the lowest path. Okay. So after we determine the path, we just pick up a sample along the path as the next starting point, as the next candidate. Okay. So then this is the first round. Then we do have a second round and the third round, and then we until we get the evading samples. Okay. So this simple description of the algorithm. The actual construction have more parameters. Please refer to the papers. So you can observe, you probably note that in order to do this, we need quite a large number of black box accessors query. For example, each sample, I need to do a morph, I need to do a test, and then I need to ask the detectors. Okay. So fortunately, we can have use some algorithmic improvement. So you may note that after all, we just need to find the gaps, the boundary. We may able to use binary search to search for the boundary and then obtain the gaps. In fact, this idea we use, we can make an improvement of that. We can do some binary search, patch binary search on the multiple path. So this essentially reduced to using about a constant number of detector per path. In the experiment, I think around 1 to 2 per path. We only need to ask the detector only twice. Okay. So experimentation results. So we conduct our experiments on two known classifiers, PDF rate and his DOS. And their first one is random decision forest based, and the other one is SVM. And they are trained with 5,000 benign samples and 5,000 malicious PDF files. And after it's been trained, we choose another 500 malicious samples to evade, to test our algorithms. Okay. There's a question on whether we should choose another 500 malicious samples for the testing, or should we use 500 malicious samples in the training data set, for evasion? Because intuitively, it's more difficult to evade the training data set. Okay, intuitively, because it's trained to reject that, so it's more difficult to evade. So we have tried both. And then we didn't see any noticeable differences. So in this paper, we report the one with using another 500 malicious samples. Okay. We compare our method with 3 algorithms. Okay. First is our proposed algorithm, we call it EvadeHC, and then a baseline algorithm, binary random. Basically, this binary random generated random path, many random path, and do a binary search on the random path to search for evading samples. In this binary random, only one detector is required for each path. Okay. And we also evaluate we also compare with another known algorithm called EvadeGP. Okay, this is a previously known method that have access to the real value confidence score from the detectors. So essentially, EvadeGP from a set of candidates choose those samples that have a low confidence score as a candidate in the next round. Okay, so right. And for the experimentation purpose, our classifier hardened by adjusting the rejection threshold. So a lower threshold will make it more difficult to evade. Okay, and we limit the search to 2,500 queries to the detectors. Then, for example, that means that for binary random, 2,500 random path is evaluated in order to find the evasion samples. So on the right is our result. Okay, you can see the evasion rate. That means the percentage of a sample that we can evade. Recall that we tested it on 500 samples. Okay, and the bottom is the malware the threshold we use in the classifier. The lower the threshold is more difficult to evade. And not as surprisingly, our method outperform the random algorithms. Okay, so at minus 0.75, we still achieve 63%, but the random binary RAM achieve only 8%. Okay, more interestingly, our method outperform EvadeGP, who supposedly use more information. That means that from the detector he get the confidence level score. Okay. So why can we be better? We suspect that because our algorithm make decision based on the tester input and the detector input, whereas EvadeGP make that decision based on the detector feedback. That means the confidence levels. Okay. So also the reject flipping distance could be a more accurate measure, okay, compared to a confidence level. So we also observed a similar result on the other classifier PDF rate. Okay. So let's look at a typical trace. Okay, a typical trace during the search process. So in the left is the x-axis is the reject flipping distance, and y-axis is the merely flipping distance. Okay, so when you plot a point, that means what is the flipping distance of that sample. Okay. So the starting sample is the diamond shape. Diamond shape is the starting samples. And then you can see that for the red line, we use 4 iterations to hit evading samples. Okay. For a sample to be evading, the reject flipping distance has to be 0. Okay, 0. And for the blue line, then he take about 8 iterations. 8 iterations to hit evading samples. Okay. The diagonal line is interesting. Is for the upper left triangles. These are the region where the merely flipping distance is larger than the reject flipping distance. So that means sample in this area is very easy to evade. Okay. So an interesting question is that if I don't use the searching algorithm, I just do a random walk. What it will look like? For that, we look at the right side of the graph. This right side of the graph gives the average flipping distance after one single morphing step. So in the right graph, the orange dot is the starting samples. So if flipping distance is about 60 and 40s, then for each blue dot, we perform one morphing step. We just perform one morphing step, and then estimate the average flipping distance of flipping distance. Then we repeat this for a few hundred times, and then we get a few hundred dots. I show that. You can see that the distribution of the average changes of the flipping distance roughly follows some Gaussian distribution. Okay. And now, if we go back to the left side, then we ask ourselves, what if we do a random walk from the starting samples, what will behave? Then we will expect that you will have a random walk based on the distribution on the right side, with the bias, with the tendency of moving along the black arrow. Okay, so so that means that in certain sense, our searching algorithm try to push, okay, the morphing towards the evading regions. So this motivates us to study a model we call an abstract hidden state morpher models. So in this model, every sample have two value A and B, and each of them correspond to the average flipping error of the reject and the Miller's flipping errors. So for every morphing step, the morpher will just output a random morph samples with the hidden value reduced according to the distribution described on the right. Okay, and the morpher is random, and yet consistent to previous output. So it's very similar to random oracle in a study of cryptography. Okay, and when we have this model, it's very useful to analyze such algorithm. For example, using it to determine the good parameters in the searching algorithm, the search algorithms. Okay. So we have also conducted quite a number of experiments. Please refer to the papers for more details. And okay, conclusions. Many evasion attacks heavily rely on domain knowledge. So we think that we believe that it's interesting to investigate the effectiveness of the evasion attacks in a genetic settings. Okay, so we formulate the evasion in the darks. So this model gives a restricted setting where the domain knowledge are contained in these three black boxes. And then from the attacker point of view, no other specific domain knowledge is required. Okay. So we also give a method to assign a meaningful real value state to the samples, and we show that evasion is possible even with binary black boxes. And although we focus on attacks, this method can be employed to enhance defense, for example, by fitting the evading samples as a training samples. Okay. So with that, I end my talk and like yes. 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 Yeah. So for this particular experiment, we limit the query to Oracle to 2,500. Yeah, for this particular example. Yeah. Okay, so we have 500 starting samples. So then we count how many we can find the evading samples. Okay. Yeah, yeah. Yes, yes, yeah. Yes, it's only 2,500. If we increase it to 5,000, then maybe the evasion rate will increase. Yeah. Yes. Oh yeah, two graphics because the parameters. Yeah. Yes. Yes. Mm. Mm. Yes. Yes. Okay, the threshold is defined is for the classifier. Then, of course, if you lower the threshold, depend how the threshold is defined. So then the acceptance rate, because there's a measurement of a false reject, false accept. So so for this, we move the threshold so that evasion is much more difficult. That means that the false reject is lower. Yeah. Yes. Yeah. Yeah. so. So yeah, yeah. So one of the steps, sorry, because it very much depend on how the threshold is defined. Yeah. Yes. 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 Oh, that okay. Yes. Yes. So for this, we didn't do experiments, but the papers actually that means the paper we sat on, they claim that small changes in the threshold doesn't significantly change the accuracy of their classifier. Yeah. Yes. 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 Okay, so first thing about transferability here. So you can view that the transferability in some sense is a global method. So you make a lot of black box query, try to reconstruct the global pictures. So in our case, is that it's a very targeted. So given a particular starting point, how do I search the locals, neighborhoods, so as to evade? So in some sense that then this, if you respect to the number of backlog requests, then this would be more efficient. And also our method is not restricted to machine learning based. So it could be a classifier based, or for example, some malware detector using a signatures, okay, of the trace or whatever. So it's not clear in those cases how is the transferability will function. Yes. Yes. Malware are all bad. All malware are bad. No, there's no good malware. Yeah. Yes. Yeah, maybe we can take offline because I do not understand much. Yes. Yeah. Yes. Yeah. Thank you.